Welcome to Month 6, the capstone of the Senior Engineer track. This session is where everything comes together. Over the next 4 hours, you'll work through distributed consensus algorithms, fault tolerance patterns, chaos engineering, and SRE practice. And you'll apply all of it in a hands-on challenge where you build a distributed system, break it deliberately, and document what happens. This is the final month. It is supposed to be the hardest. The 4 hours break down into 4 focused blocks. The first hour is distributed systems fundamentals, CAP theorem as a decision tool, then Raft and Paxos in depth. Hour 2 moves to fault tolerance, circuit breakers, bulkheads, retree patterns, and a failover architecture workshop. Hour 3 is implementation. You'll build a 3-node distributed configuration service with leader election and replication. Hour 4 is chaos engineering. You'll design experiments, inject failures, and present your reliability findings before track graduation. 5 things you will be able to do by the end of this session. First, implement distributed consensus, choosing the right algorithm for leader election or data replication. Second, fault-tolerant systems using circuit breakers, bulkheads, and retree with backoff. Third, conduct chaos engineering experiments the right way, hypothesis-driven, measured, and documented. Fourth, create SRE runbooks with SLOs, golden signal dashboards, and incident response playbooks. Fifth, build and demonstrate automatic failover with quorum-based split brain prevention. This is also month 6 of 6, the final session of the Senior Engineer track, with a graduation requirement of 75%, average across all months. The CAP theorem states that a distributed data store can guarantee at most 2 of 3 properties: consistency, availability, and partition tolerance. The critical insight is that network partitions are not optional in real distributed systems, they happen. Which means the real choice you make when selecting a data store is always between CP and AP. CA systems, consistent and available, tolerating no partitions, exist only as single-node deployments. The moment you add a replica, you're in partition territory. CP systems like etcd and Zookeeper refuse to serve reads during a partition rather than return stale data. AP systems like Cassandra and DynamoDB keep serving requests during a partition, accepting temporary divergence across nodes. DNS is the classic AP example. It serves cached data, even when it may be outdated. The POSLT extension adds another dimension. Even without a partition, you're trading off between latency and consistency. Strong consistency requires cross-node coordination, and that takes time. Raft was designed to be understandable, and its state machine is clean. Every node starts as a follower, waiting for heartbeats from a leader. If no heartbeat arrives within the election timeout, randomized between 150 and 300 milliseconds, the follower promotes itself to candidate, increments its term, votes for itself, and sends request vote calls to all peers. To win, it needs a majority. In a 3-node cluster, 2 votes. A node grants its vote to the first candidate it hears from in each term, provided that candidate's log is at least as current as its own. Once elected, the leader sends append entries calls to all followers. These calls serve dual purpose. They replicate log entries, and they are the heartbeat. An entry commits when a majority acknowledge it. If the leader dies mid-replication, followers time out and start a new election. The essential persisted state is 3 fields: current term, voted for, and the log. These 3 fields, written to disk before any acknowledgement, are everything Raft needs to recover correctly from a crash. Paxos is the ancestor of modern consensus algorithms. It has 2 phases. In the prepare phase, A proposer broadcasts a proposal number to acceptors, and they promise not to accept lower-numbered proposals. In the accept phase, the proposer sends its value, and the value commits when a majority accept it. Paxos is theoretically sound, but notoriously difficult to implement correctly for a full replicated log, which is precisely why Raft was designed as a more understandable alternative. Gossip is a different class of protocol entirely. Each node periodically picks a random set of peers and exchanges state. Information spreads exponentially, reaching all nodes in O log n rounds, with no single point of failure and no coordinator. Cassandra uses gossip for cluster membership. Consul uses it for health propagation. It is eventually consistent and not suitable for linearizable writes, but it is highly scalable and resilient to network partitions. Byzantine fault tolerance solves a harder problem: nodes that behave arbitrarily or maliciously, not just nodes that crash. PBFT requires 3 f+1 nodes to tolerate f Byzantine faults and produces n² messages per consensus round. You see it in blockchain systems, not in typical distributed services. 4 patterns form the core toolkit for preventing single failures from cascading into full outages. The circuit breaker wraps calls to a dependency. After a threshold of consecutive failures, it opens and immediately rejects further calls without attempting the downstream request. This prevents a slow or failing dependency from exhausting your thread pool. After a cooldown, the breaker enters half-open state and allows one test request through before deciding to close or remain open. The bulkhead pattern isolates resources per dependency, separate thread pools, separate connection pools. A failure in your payment service that exhausts its 50 threads cannot steal threads from your inventory service if they run in separate pools. The name comes from ship compartments designed to prevent flooding from spreading. Retry with exponential back-off handles transient failures. Retry with delays of 1, 2, 4, 8 seconds, adding jitter, a small random offset, to each delay. Without jitter, every client that hit the same failure retries at the same instant and recreates the overload. And every outbound call must have a hard timeout. A thread blocking indefinitely on a slow database is one of the most common cascade failure mechanisms in production. 3 pitfalls with retry that you need to know before you implement it. First, never retry on client errors. A 400 bad request means your payload is wrong. Retrying sends the same bad request again and again. Retry only on server errors and network timeouts. Second, no jitter causes thundering herd. Without the random offset, 1,000 clients back off to the same interval and retry simultaneously, re-overloading a service that was just beginning to recover. Always add jitter. 10 to 25% of the base delay is enough. Third, retrying non-idempotent operations creates duplicate side effects. If you retry a POST that creates an order and the original request was processed, but the response timed out, you create 2 orders. The fix is an idempotency key, a UUID per request sent as a header. The server stores the result by that key for 24 hours and returns the cached response on any duplicate submission. Use bulkhead and circuit breaker together. Bulkhead limits blast radius by containing which resources are affected. Circuit breaker limits hang time by cutting off calls early. Each addresses what the other misses. The Google SRE book identifies 4 signals that, between them, capture almost everything important about a system's health. Latency measures how long requests take. Track both successful and failed request latency separately. A request that fails quickly is very different from one that times out after 30 seconds. Alert on P99, not the mean, because tail latency is what real users experience. Traffic measures the demand on your system, requests per second or transactions per second. A sudden drop can be as important as a spike. It may mean traffic silently shifted away from a degraded service. Errors measures the rate of failed requests. Explicit 500 errors, implicit wrong content 200s, and policy-based failures like latency SLO violations. Error rate directly burns your error budget. Saturation measures resource utilization, CPU, memory, disk, network. Little's law tells you that 80% utilization, latency begins degrading non-linearly. Alert before you hit capacity, not after. Chaos engineering is not about breaking things randomly. It is a scientific discipline for empirically validating that your system can withstand production turbulence. The methodology has 5 steps. First, define steady state, concrete, measurable normal behavior, 99.9% availability, P99 write latency under 100 milliseconds, 0 error rate. Without this baseline, you have no way to tell whether an experiment changed anything. Second, form a specific hypothesis. Not what happens when the leader dies, but when the leader fails. A new leader is elected within 10 seconds. No data is lost, and client errors resolve in under 15 seconds. Third, introduce real-world variables, node crashes, network partitions, packet loss, resource exhaustion, clock skew, dependency failures. Fourth, run in production with guardrails. Start in staging, define blast radius, have a kill switch, and gradually move toward production where unknown unknowns live. Fifth, automate and run continuously. A one-time chaos exercise is a snapshot. New deployments introduce regressions. Scheduled experiments catch them. Your Capstone Challenge is a distributed configuration management service, a 3-node key-value store with a full consensus layer. You'll implement Raft-inspired leader election and write replication. The cluster must survive a single node failure with automatic failover in under 10 seconds. You'll instrument it with Prometheus metrics covering latency, errors, replication lag, and leader elections. And you'll run 4 documented chaos experiments, each following a hypothesis method observation verdict structure. 100 points total, divided equally across 4 deliverables. 75 points passes the challenge. 90 or above signals production-ready thinking. You have 3 hours of in-session implementation time, plus take-home time for documentation. This is a genuine engineering problem. Not a toy exercise, it tests consensus, fault tolerance, observability, and operational thinking simultaneously. Part 1 of the challenge covers the core system, 25 points. Leader election means implementing the full follower-to-candidate-to-leader transition. Persist the current term and voted for to disk, so that a crashed node cannot vote twice in the same term after restart. Use randomized election timeouts between 150 and 300 milliseconds to resolve split votes naturally. Data replication means writes go to the leader, which replicates to followers before committing. An entry commits when 2 of the 3 nodes acknowledge it. Followers reject writes and redirect clients to the current leader. Linearizable reads require the leader to verify quorum before serving. This prevents a partitioned X leader from returning stale data. Expose a status endpoint on every node reporting its current state, term, and known leader. The REST API needs 4 endpoints: Put to write a config key, GET to read it, GET status, and Post to trigger an election for testing. The entire cluster must come up with a single Docker compose up command. Part 2 requires 4 documented experiments, 25 points. Experiment 1. Kill the leader. Hypothesis. New leader elected within 10 seconds, 0 data loss. Measure detection time, election time, and time to first successful client write on the new leader. These are 3 separate phases with different implications. Experiment 2. Network partition. Disconnect one node. Hypothesis. The isolated node must refuse writes because it cannot achieve quorum. This directly tests whether your quorum check is enforced, not just theoretically present. Experiment 3. Cascading failure. Down a downstream dependency. Hypothesis. The circuit breaker activates and upstream services degrade gracefully rather than failing completely. Experiment 4. Resource exhaustion. Constrain a node to 128 megabytes of memory using Docker update. Hypothesis. The system degrades gracefully. The constrained node slows down, but does not corrupt data or cause a cascade. Every experiment must include measured timings, not just narrative descriptions. Numbers are evidence. Words are not. Part 3 demonstrates that failover actually works in practice. 25 points. 3 scenarios. Planned failover. Gracefully step down the current leader via an admin endpoint. With a proper retry mechanism in the client, the impact on write throughput should be near zero. Measure it. Unplanned failure. Kill the leader with Docker kill. No graceful shutdown. Run a continuous write workload before, during, and after the failure. The target is 0 lost writes. Any entry that received majority acknowledgement before the crash must survive. Measure detection time, election time, total recovery time, and actual lost write count. Split brain prevention. Isolate node 3 from the network and verify explicitly rejects writes. Then heal the partition and verify data converges across all 3 nodes. At no point should 2 nodes both believe they have write authority. The evaluation looks for architecture clarity, demonstration completeness, recovery time objectives met, data integrity proof, and documentation quality. Part 4 is your operational documentation. 25 points. Define SLOs with error budgets. 99.9% availability means 43.2 minutes of allowable downtime per 30-day month. Write latency P99 under 100 milliseconds means 0.1% of writes may exceed that threshold. Data durability at 99.99% leaves almost no tolerance for data loss. Your monitoring section needs dashboard references, key metrics with normal warning, and critical thresholds and 4 alert definitions. Node down at P2, leader flapping at P1, replication lag at P2, error rate high at P1. P1 wakes someone up. P2 opens a ticket. The triage checklist is a structured first response procedure. Check node status, verify leader health, review consensus metrics, check recent deployments, check dependencies, in that order. And 3 full runbooks covering leader not elected, replication lag, and split brain, each with symptoms, diagnosis commands, resolution steps, and a post-incident checklist. 4 deliverables, each worth 25 points. A zipped repository name with your name and month 6 prototype, then 3 markdown files for chaos, failover, and runbook. The submission checklist is your minimum bar, cluster running and demonstrable, 4 chaos experiments complete, failover documented with metrics, runbook covering all 3 incident types, all files named correctly. The 4 grade bands set the expectations clearly. Exceptional, 90 or above, means production-ready code and documentation, automated chaos tests, full SLO tracking, and genuine operational thinking that goes beyond the requirements. Proficient, 75 to 89, is solid engineering, functioning leader election, all 4 experiments, a complete runbook. Developing, 60 to 74, means the core works, but some experiments are shallow or the runbook is incomplete. Below 60 requires resubmission before you can complete the track. 3 concepts that are often confused. An SLI, service level indicator, is what you actually measure: observed success rate, measured latency. An SLO, service level objective, is your internal target, 99.9% availability. An SLA, service level agreement, is your contractual commitment to customers, always set lower than your SLO by a safety margin, and always carrying a penalty for breach. The error budget is the operational tool. 100% minus 99.9% is 0.1%, which for a 30-day month equals 43.2 minutes. That budget covers planned maintenance, incidents, and your chaos experiments. The error budget policy shown here is what makes this work. When the budget runs out, feature releases stop, and all engineering attention goes to reliability. This directly aligns product incentives with operational health. Burn rate alerting manages the budget in real time. A fast burn at 14 times normal rate over 1 hour triggers an immediate page. A slow burn at 6 times normal over 6 hours opens a ticket. Both alerts are needed because different failure modes show up at different time scales. You have completed all 6 months of the Senior Engineer track. Across this program, you've developed high-scale system design and architecture, event-driven and distributed systems, performance optimization and capacity planning, security best practices and threat modeling, technical leadership and mentoring, and now distributed systems, SRE, and chaos engineering. These skills are what distinguish engineers who build systems from engineers who build systems that survive production at scale. 3 next steps. Schedule your promotion assessment with your engineering manager. Consider the tech lead track if leadership development is your next growth area, and lead a production reliability project to apply what you've built today in a real environment. Graduation requires 75% average across all 6 months, all deliverables submitted, and demonstrated ability to mentor a colleague on distributed systems topics. That last requirement is deliberate. You don't fully understand something until you can teach it.